Good afternoon all. Today's topic is translation, look-aside buffering, paging. And the last video I explained paging, the non-contiguous memory allocation and general techniques of paging. Here implementation of page table. We know what is page table. With the help of page table, we are converting our logical address into physical address. So page table will be having that frame numbers, and page table is kept in the main memory only, and there are two registers to support page table. Those two registers are page table base register and page table length register. Page table base register points to the page table. Page table length register indicate the size of the page table. In this scheme, every data or instruction access require two memory access, one for page table and one for the data or instruction. The two memory access problem can be solved by the use of super fast lookup hardware cache called translation look-aside buffers, also called associative memory. And here memory, there are your page table will be there in the main memory only, right? Page table is located in the main memory only. So there are two memory access. If you apply this particular method using page table, there are two memory access. Why two memory access, or how two memory access is like first your logical address is divided into two parts, P and D. P is the page number. Using page number, you have to access page table content, right? So the page table will be there in the main memory. So to access page table, one memory access. After getting the frame number, you have to access your own data from the main memory. So again one more memory access. So total two memory access. Memory it is more time consuming. So to how to reduce this two memory access to one memory access, that is with the help of translation look-aside buffer. Translation look-aside buffer is a special fast lookup hardware, and it's also known as associative memory. So there are two memory access if you are using normal page table. One to access page table, another one to access your own data. Page table will be there in the main memory only. So to access page table, one memory access, and from page table the content, to access this content, again one memory access. So translation look-aside buffer is some TLB store address space identifiers in each TLB entry, uniquely identifies each process to provide address space protection for that process. TLB is typically very small, and on a TLB means value is loaded into the TLB for faster access next day. Replacement policies must be considered, and some entries can be word down for permanent fast access. And TLB, this is the this is how your TLB looks like. TLB has two columns. First column for page number, another column for frame number, and you have to search your TLB. Address translation. If P is in associative register, get frame number from that. Otherwise, get frame number from the page table in memory. Let me explain these two slides with the help of the diagram. See. This is enhanced version of our first paging diagram. Here we have included TLB. And I told you TLB has two columns, one column for page number, another column for frame number. So how this diagram works, like your logical address is divided into two parts. First part is page number, second part is offset. And page number is using page number, you can search your TLB, whether that page number is available in the TLB or not. If the page number is available in the TLB, go to the corresponding column of frame number, get the frame number. Using that frame number and your offset, you can access your actual data from the physical memory. That is the first step. If you are when you are searching TLB using your page number, if the data is not available in the TLB, then you have to go to page table, and page table the data, the frame number you will get from the page table, and using that frame number and offset, you can access your actual data. So there are two, either you can go through this way or this way. If the data is there in the TLB, we are going this way. If the data is there not there in the TLB, we are going through page table. So if the page number is available in the TLB, then it is known as TLB hit. If the page number is not available in the TLB, it is known as TLB miss. So TLB hit means we are not touching page table. We are not touching page table if it is TLB hit. TLB hit indicate that page number is available in the TLB. Page number is not available in the TLB means it is TLB miss. So we are accessing your frame number with the help of the page table. This is the flow chart. Search in the TLB, required entry in TLB. If S means we are not touching the page table, directly we are going and accessing our physical address. If the data is not there in the TLB, access the page table, update TLB. After accessing the page table, you can update the TLB. Then it will be useful for the next time. Then generate your physical address. So here you are not touching the page table, right? So only one memory access to access your physical address. Here you are touching the page table. So to access page table, one memory access. To access your actual data, also one memory access. So total 2 memory access. Page table will be there in the main memory only. So total 2 memory access. And how to calculate effective access time. There is a formula to access effective access time. Hit ratio of TLB into access time of TLB plus access time of main memory plus miss ratio of TLB into access time of TLB plus 2 into access time of main memory. Hit ratio and miss ratio is if the data is there in the TLB, that how many times the data will be there in the TLB, that is the hit ratio. How many times the data is not there in the TLB, that is the miss ratio. If you know the hit ratio, it is easy to calculate miss ratio. 100 minus hit ratio is miss ratio. One example is hit ratio is percentage of times that a page number is found in the TLB. 80% hit ratio means that we find the desired page number in the TLB 80% of the time. Suppose that 10 nanosecond to the access memory. If we find the desired page in the TLB, then mapped memory access take 10 nanosecond. Otherwise, we need 2 memory access time. I'll explain it. See. Here we are considering access time of TLB is very less. So we are not taking that value. We are taking it as 0. Access time of TLB compared to access time of main memory is very less. So we are taking it as 0. So hit ratio. Hit ratio is given 80%. 80% means 0.8. 0.8 will be the hit ratio. So 0.8 into 0.8 into this one we are taking as 0. It is very less compared to access time of main memory. So this one we are taking as 0. So 0.8 into 0 plus access time of main memory is given. Access time of main memory is 10 nanosecond. So 0.8 into 0 plus 10. 0.8 into 0 plus 10 is 10 plus miss ratio of TLB. Miss ratio of TLB is 100 minus 80% or 80%. So 20%. Miss ratio is 0.20. So 0.20 into access time of TLB is very less. We are taking a 0 plus 2 into access time. 2 into 10. Access time of main memory is 10. So 2 into 10 is 20. See here 0.80 into 10 plus 0.20 into 20. Why 2 times here? Why 2 into 10? 2 into 10 is because first time you have to access the page table, then you have to access your actual data. So 2 times memory access. If it is there, this is TLB hit, this is for TLB miss. TLB hit means only one memory access, TLB here miss means 2 memory access. One more example, if your hit ratio is 99%. Hit ratio is 99% means here 99, here will be 0.01 and only one memory access, so into 10, here 2 memory access, so into 2 into 10, so 20. Memory protection. Memory protection implemented by associating protection with each frame to indicate if read, whether the frame is read only or read or write or only execute, or to indicate that there is one separate bit along with the frame number. And one more bit is there in a page table. That bit is known as valid invalid bit to check whether you are accessing valid data or invalid data. Valid indicate that the associated page is in the process logic address space and is thus legal page. Invalid indicates that the page is not in the process logical address space or use page table length register. Any violation results in a trapped kernel. I'll explain it with the help of the diagram. See, this is your page table. There are one extra column. That column is for valid invalid bit. We indicate valid bit. I indicate invalid bit. So 0 to indicate page 0 will be there in the frame 2. Page 0 will be there in the frame 2. Correct. So valid. Page 1 will be there in the frame 3. Correct. So valid. Page 2 will be there in the frame 4. Correct. Valid. Page 4 will be there in the frame 8. That also correct. Page 6 will be there in the page 6. Do you have page 6 here? No. So page 6 is not there along with my program. So we are trying to access invalid page. So this I indicate it is invalid. Page 6 is not there with my program.